as its propagating principle. So optic represents light waves or light signals transmitted over a closed medium. So which we use in fiber. It could be either a glass made fiber or it could be a plastic made fibers. So in olden days they had used glass made fibers, halide fibers, chalcogen fibers for fabricating the core and cladding of the optical material being used as the medium. So due to the heavy cost of that, they had migrated from glass, halide, chalcogen fibers to nowadays POFs, plastic optical fibers, which uses the polymer. Okay. So when we use this type of mediums as the channel, so as the distance increases between the transmitter and receiver, the optical signal whichever passes through that gets attenuated or gets degraded. Degraded in the sense, if you are sending 10 watts of power at your transmitter, you will be getting the power which is not equal to 10 watts. It would be definitely less than 10 watts of power. So some part of your signal is being absorbed or reflected or refracted along the optical cable length. So the length may vary. So as distance increases, the signal degradation also increases. So degradation is that loss of information or loss of signals. Okay, I think in Saturday we had done an experiment in laboratory. So you would have chosen an CW laser. I think fiber optic software was being used. You had taken an CW laser, then you had put in fiber length at some distance, 100 kilometer, 200 or 300, whatever might be, you can put it. Then you run the program or you simulate the program and analyze how much amount of power is being obtained at transmitter and receiver. Placing your power meters at transmitter and receiver, you'll be able to see that. So you can able to see that whatever the power that you are transmitted will not be equal at the received. A demo was shown on Saturday, so you can follow that. So in that you vary the length of the fiber. Initially you take 100 meter, see the input power, see the output power. Then you vary it for 1000 meter, which is 1 kilometer. See the input power, see the output power. Make a note. And then you vary it for 3 kilometer, 4 kilometer, 10, 15, 20, till 100 kilometers. You try it and see. As the distance of the optical fiber increases, the input power will remain same, but the output power will gradually decrease. Okay, which we call as degradation. Since the signals which have been transmitted gets degraded, we need to analyze how it gets degraded, in what way, in what fashion, in what ratio. Okay, which we are going to see in this unit. So the contents or the outline for this presentation start with attenuation. The attenuation is followed by absorption losses, scattering loss, bending loss, core cladding losses. These 5 losses comes under attenuation. Absorption loss, scattering loss, bending loss, core and cladding losses. Next, what we are going to see is the signal distortion. Signal distortion in optical waveguides. So this is determined by the information capacity determination along with its group delay, which is divided into 2 different distortions. One is material dispersion Next one is waveguide dispersion. The waveguide should come together, wave and the guide. There is no space. Let me recorrect it. Material dispersion and waveguide dispersion. So after the two different types of dispersions, which is a type of signal distortion in optical waveguides, we are going to see a special case of the signal distortion in SM fibers, which is a single mode fibers, which is polarization mode dispersion, PMD. In that we have another type of distortion called as intermodal dispersion and intramodal dispersion. Then, as we have seen in single mode fibers, we are going to see the same in terms of graded index fibers. The pulse broadening of the optical signal in a special graded index fiber. Then followed by mode coupling, where we will be designing and a single mode fibers, its refractive index profile and cutoff wavelength determination. So these are the contents in unit 2 and in our presentation also. So to start with attenuation, okay. First we'll define what is this attenuation is, and what is this distortion is. Then we'll go in depth of attenuation and distortion. So first question is that what are the losses or signal attenuation mechanisms in an optical fiber during the transmission of optical signals? Why and to what degree do optical signals get distorted as they propagate down a fiber? So for these two questions, the answers is your unit number 2 fully. Okay. What are the losses or signal attenuation mechanisms in optical fiber? This first one is the signal attenuation or the fiber loss. Second one is the signal distortion. So why and to what degree does this optical signal gets distorted is what we are going to determine in specific cases. In graded index and in pulse mode dispersion. So let us see what is this attenuation is. So attenuation determines the maximum repeaterless separation between optical transmitter and receiver. Maximum repeaterless separation between optical transmitter and receiver. So in an optical communication system, we have a transmitter section, we have a receiver section. So this signal attenuation determines the maximum separation of them as fiber losses. So signal distortion will cause the optical pulses to broaden. Rather than narrowing, it broadens as they travel along the fiber. Then in some cases they overlap between the neighboring pulses, creating errors in the output, thus resulting in the limitation of information carrying capacity of the fiber. So a pulse will be moving in one wavelength, second pulse will be moving in another wavelength, third pulse will be moving in another wavelength, fourth, and so in sequences. So due to the broadening of any one of the signal, for example, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, lambda 7, lambda 8 are the pulses which are being moving. Suddenly lambda 3 and lambda 5 gets broadened. What will happen is that this lambda 3 gets overlapped with the lambda 2 and lambda 4, whereas lambda 5 gets overlapped with lambda 4 and lambda 6. So here distortion occurs in this case, so which creates errors in at the receiver in retrieving these signals. In the place of retrieving lambda 3, I may retrieve lambda 4, or in the place of retrieving lambda 4, I may retrieve lambda 3 or lambda 5, because pulse broadening has occurred in lambda 5 and lambda 4. As a result, lambda 4 gets affected more, lambda 2 lesser, lambda 6 lesser. So the overlapping between the neighboring cells will create errors. So now let us see this attenuation or fiber loss. So the power loss along a fiber is called as attenuation, which is determined by the fiber attenuation coefficient measured in amperes per kilometer. Okay. So how do I find is that P of 0 is at the initial stage, P of 0 is at the initial stage, this is your transmitter, this is your receiver. So in between there is a brown color line or maroonish color straight line, which is the optical cable. So this optical cable is laid at a distance of L. So Z is equal to 0 is that the power is measured at the transmitter or at the starting point. Z is equal to L is the point where the optical fiber gets terminated or the receiver point is reached. So Z is equal to L. So at that distance. So the measurement of power P0 is at transmitter and the PL is at a distance of L. Okay. So then we can find the power loss along the, or you can find the power which is present as of L is equal to P of naught into exponential e power minus AP into L. L is AP into L. So L is the length of the optical fiber along which the optical signals has traveled. So this in terms of lengths or P of Z can be written as P of naught into e power minus alpha P into Z. So where alpha P is the fiber attenuation coefficient. So which is derived by, as the distance increases, the attenuation is exponential to its length. Okay. So this alpha P can be determined by alpha, which is measured in decibels per kilometer, is equal to 10 divided by L. So L is the length of the fiber. Log of P0 divided by PL. So for 1 kilometer, the attenuation factor is 4.343 alpha P per 1 decibel per kilometer. So this is formula for finding attenuation. Next is fiber loss in decibels per kilometer, which we had found. The representations in decibels per meter or decibels per kilometer. So power at the receiver or along the fiber having a distance of L in decibels per meter is equal to P0 of dBm minus alpha dB by kilometer into L, the length. Where dBm is the decibels milliwatt which is equal to 10 log P power measured in milliwatts. This is the optical fiber at curve versus the wavelength curve, which is deployed for all the three windows that we had seen in last class. First window, second window, and the third window. Okay, so the first window is operating at 850 nanometer. Okay, this is the first window. Yeah, sorry for the interruption. So we were seeing this optical fiber attenuation versus wavelength. So the wavelength is being given in x-axis. Attenuation being measured is given in y-axis, ranging from 0.1 to 20 decibels per kilometer. For every kilometer is being taken. So the first window, it comes under your uh, first evolution of optical fibers. The first window system, which was uh, came in evolution during 1970s, as we had seen in uh, generation or evolution of optical fiber. The first window system gave attenuation around, you can see that it is around 7 decibels per every kilometer, meaning that for every kilometer 7 decibel of signal will be lost. So then, okay, this was operating at around 850 nanometers, 850 nanometer wavelength. Lambda is equal to 850 nanometer. Around this it was being used. So then they had shifted to the second window due to the evolution of technology or movement towards the higher wavelengths. Okay, then they had gone for second window system. In the second window system, which operated at 1330 nanometer, 1330 nanometer, which is the second window, the attenuation was less than 1 decibels per kilometer. You can say that it is merely 0.9 decibels per kilometer, second window, operating at 1330 nanometer. So then the second window was done during 1980s. Then in 1995 or 1996, the third window was being implemented, which was operating at 1550 nanometer, 1550 nanometer, third window, around that. And the attenuation was around 0.8 decibels per kilometer. So for 1 kilometer it was 0.8, and if it is for 10 kilometers it would be 80, and it goes on depending upon the length of the fiber being used. So this dark line which is traveling in this, and there was a peak after the 1330 nanometer usage, they had shifted to 1400 nanometer, so in which the attenuation was very much higher as compared to the second window. So then only they shifted to this 1550 nanometer. So this is the standard fibers attenuation curve. You can see that this dark line which passes, written as standard fiber, goes here, goes like this. So this is your all wave fiber exponentially. Okay. So this graph represents the optical fiber attenuation versus wavelength. So any queries in attenuation till now? It is a measure of signal attenuation with respect to distance. So as the distance increases, the amplitude of the optical wave tends to decrease. So that we call it as attenuation. So any queries? If anything is a type in chat box, because next I'm going to start another topic. Okay, thank you, Mukesh Sai. Thank you, Sai Ganesh. No queries. we do have an experiment in the optical communication to find attenuation also. So we'll do that. So when you do that also, you'll be understanding this concept in a more better way. Okay. Physically or in simulation also. Okay, still no queries. So I proceed on to the next topic called absorption. So absorption is caused by three different mechanisms. One is the impurities present in the fibers. Second one, intrinsic absorption. Third one, radiation effects. Okay. So what are these things? We'll see. So first of all, I'll tell you where this absorption occurs. Okay. So this absorption occurs just a minute. I'll draw and I'll show you. Yeah, this black color indicates. Let me write. This black is your core. This is your cladding. Okay, as we had seen in the mode theory, core and cladding. So we are going to draw references. Okay, draw your reference. The red is the reference. This is the reference. So now I choose TE. Now I choose T0. Okay. So if I choose T0, what will happen? I'll be having 0 crossings. So I'll draw like this. So here the green color indicates the field pattern. So the field pattern has 0 crossings. So if this has 0 crossings, what will happen is that here the optical wave that it travels will have maximum field in this region, which I'm drawing in. I'll draw it in yellow color. If I'm drawing it in yellow color, so this region will have maximum field propagation. So this area is your maximum field propagation. Okay, which is along the core axis. It is along the core of the fiber. And the core of the fiber. You can see that when this wave travels, the optical wave travels along the core of the fiber, there is maximum intensity. So now see at the edges of the core or the field pattern which I am drawing here. A portion of the field pattern or the optical wave also passes into the cladding. You can see that. Wait a minute. Just a minute. I'll show you that in yellow color. You can see that the optical wave passes through the cladding here and here in T0. So the optical wave passes fully here. So means that the wave which I decide to go in T0 mode, it is passing along the core of the axis with maximum intensity, but some portion of light is being falling into the cladding. So which gets refracted. I'll show you in bold. Just a minute. So the waves gets refracted here. Refracted. So this also gets refracted. So if it is reflected, the wave will pass in this way. Is it refracted? If reflected, now if I'm having a reflected wave, so the wave will move in this fashion. It is reflected. Okay. So due to this refraction or the refracted signal which is passing into the cladding, the phenomena of absorption occurs. Meaning is that this cladding will absorb some optical wave. This cladding will absorb some optical wave. The fiber, the outer jacket or the buffer will absorb some optical wave. So which is all due to the absorption. Okay. Let me save this file, then I'll be back. It is due to absorption. So the field pattern diagram that I had drawn for TE0 is an example of absorption. So I think now we have got an idea of what absorption is. Okay, let us see absorption. So why does this absorption occurs? Is that it is due to, it could be due to three different mechanisms. One is the fiber which was made would be having impurities. Okay, impurities is that when you make a fiber manufacturing or fabricating a fiber, you need to add some dopants in order to make the bonding of fibers. So adding impurities to the pure material is always a fashion, or is always undergone in semiconductors and in optical fiber manufacturing also. So this adding dopants should be appropriate, particularly when you add this transition metal ions, the OH ions, which are having absorption peaks at uh, 2700 nanometer, 400 nanometer, 950 nanometer, and 725 nanometer. When you add these OH ions into the fiber fabrication, you should carefully add, or else it will create more absorption, more amount of light wave that is being traveling along the fiber gets absorbed. So in turn, it gets refracted. The light wave which is passing inside the core gets refracted away. Okay, so the wavelengths which are given here are especially for the OH ions that are being used as a dopants in fabrication of the fiber material. So next mechanism that is meant that creates absorption is that intrinsic absorption. So intrinsic absorption is that the electronic band absorption, the UV region, the atomic bond vibration band IR region, which is present in the silicon oxide or the silica, will by defaultly absorb when the light region is being traveled with this. Then third one is the radiation effects. So due to overheating, due to exposure to climatic conditions, the optical fiber will radiate such that it will absorb the optic signals. It is traveling from one end to another end. So these are the three different mechanisms that are responsible for absorption. Next loss that we are going to see is scattering loss. So scattering loss is that you all are familiar. So this scattering loss occurs due to the scattering of optical wavelength or optical light that falls on the materials. For example, I'll explain this with an real example. When you take a prism, you have a prism, take it. So on the prism, you pass a light. You pass a white light. So at the other sides of the prism, you can able to see 7 different lights being appearing from white light. So that experiment you would have done in your junior college level or at your engineering physics laboratory. Prism. So when you keep the prism at the light side, the other two sides you can able to see the different colors of that white light, which is Vibgyor. So here the scattering law is being explained. Okay, what is scattering is that when light falls on some materials, it gets scattered away, just like put a drop of water onto the floor surface. What will happen? It will move away from the point of direction. So we put at the point of direction, the water, when a water droplet is being falling on the surface, it gets split up. So that is scattering. So in the same way, the optical signals will tend to scatter, which is following a certain principle. So that principle is Rayleigh scattering. So the Rayleigh scattering is law is 1 by lambda power 4. 1 divided by lambda power 4 or lambda power minus 4. Both the same. So the small variations in material density, the fiber material that we are taking, the chemical composition that we are using for manufacturing, and the structural inhomogeneity, the combinations of the different fibers being used for fabrication, inhomogeneity structure. This tends to scatter light in other directions. Rather than moving it in a same direction, it will scatter in the other directions. Okay, and thus absorb energy from the guided optical wave. So this mechanism is called as scattering, and it follows Rayleigh scattering law. So this Rayleigh scattering law is 1 divided by lambda power 4, which is always valid for wavelengths having greater than 5 micrometer. So obviously we are using the wavelengths beyond 5 micrometer only. So the attenuation coefficient due to Rayleigh scattering is approximately proportional to 1 divided by lambda power 4 or lambda power minus 4 scattering loss. So this scattering loss also can be given in the formula as such. The attenuation of the fibers at around 1.3 and 1.55 micrometer can be exactly predicted by Planck's constant or the Planck's formula. So therefore the scattering loss due to scattering is directly proportional to lambda power minus 5, the exponential of hc divided by lambda kb t, the whole inverse, or 1 divided by exponential of hc divided by lambda kb into t. So where h is the Planck's constant, 6.626 into 10 power minus 34 joule seconds. kb is the Boltzmann constant, which is 1.3806 into 10 power minus 23 joule per Kelvin, and T is the temperature at which this optical fiber is being operating, and lambda is the wavelength of operation. So by this we can easily find the scattering loss. So here is an illustration of the optical fiber attenuation characteristics of low loss, low OH in silica fibers. You can see that the upper is indicated with the wavelength measured in micrometers, 0.5 to 10 micrometers, or you can manipulate this in nanometers also. Okay. Then losses, right, from 0.01 to 100, and the photons of energy being absorbed from 2.5 to 0. Okay. Photon energy is what? The light waves propagate. The light propagates in terms of photons of energies, or bundles of packets of energy called as photons. So the absorption loss in infrared region is this. It's dark dotted red. The absorption loss in ultraviolet region is this. This maroon dotted. For different photons of energy at different losses at different wavelengths. And this is your scattering loss. So this line is your scattering loss, and this is your measured loss of fiber from first window to second window, then third window. So any queries in this scattering loss and absorption loss, you can type in chat box. I'll give you 4 or 5 minutes of time. You can discuss. If any queries, you can type in chat box. Then I'll proceed on to the next topic. Okay, since no queries, thank you, Sai Ganesh. We proceed on to the spectrum in terms of wavelength for single mode fibers. So I'll show you the attenuation as well as scattering for single mode fibers. So when a single mode fiber is being used with the wavelength from 1100 to 1800 nanometer wavelengths, the attenuation and the scattering and absorption. I'll show you. You can see that from the diagram. The intrinsic scattering due to Rayleigh Scattering Law for 1100 nanometer, it is around here in this point. Okay, it would be around 0.2, 0.3, 0.4, 0.5, 0.6 decibels per kilometer. And at around 1200 nanometer, it is 0.3 decibels per kilometer. Intrinsic scattering. And at around 1400 nanometer, it is 0.2 nanometer. And you can see that at around 1550 or 1600, it is nearly 0.15 decibels per kilometer. The intrinsic scattering. And beyond 1600 nanometer, we don't get intrinsic scattering. In turn, we get intrinsic absorption. Okay, the intrinsic absorption that we had seen. So where most of the optical wave signals gets absorbed in practice. So here at the above there is a striped line, cross striped line is a typical range. Okay, as we had seen with respect to the graph, the first window, second window, the desired single mode fiber structure. Okay, the typical range. So this at this wavelength, the typical range should be here. At 1400 should be here. At 1500 should be here, and after that it should increase like this. So this is a typical wave showing the absorption, scattering, and attenuation characteristics in single mode fiber. So next is an important concept called bending losses. They are classified into two different types. One is macro bending, second one micro bending. So what is this macro bending and what is this micro bending? Is that the optical fiber is cylindrical in nature, which travels at a long distance, is known to all. So the curvature of the bend is much larger than the fiber diameter. Okay, the curvature of the bend. So what is that bend? Is this? So this is your bend. So this is your optical fiber. It is being bent. Okay, it's being bent. So the curvature of the bend is larger than the fiber diameter. For example, if the fiber diameter is 10 micron, and the bend is beyond 10 micron, then micro bending loss will occur. So if that is the case, the light wave suffers severe loss, severe loss due to radiation of the optical field in the cladding region. The optical field or the field which is being propagating along that core will experience more losses due to this bending. Okay. So if this radius of curvature decreases, the The loss increases exponentially until it reaches a certain critical radius. So the bending can be allowed only to a certain level, not more than that. So for any radius smaller than this point, the losses suddenly becomes extremely larger, and the higher order modes radiate away faster than the lower order modes. So due to this macro bending, we'll be having lower order modes such as TE0, TE1, TE2, TE3, TE5, which are the lower order modes. The higher order modes are your TE9, TE11, TE12, TE13, 15, TE17, TE21. So these are considered your higher modes. So due to this bending, this lower modes, which is having a lower distortion, will tends to fade away. Means it will move into the cladding. Whereas the higher order modes, which is having more distortion, will pass through the optical fiber. Okay, so this is the result of macro bending. Macro bending occurs. So this is the example of macro bending. So this is your fiber. This is the radius of curvature R, capital R. So we have an field distribution of the optical wave. So it is moving. So this is your curved fiber. Okay, here this is the power being lost. So you might be asking, if it is bending, how power will be lost? So the fiber which is going in this direction tends to turn in this direction. So the optical wave that travels like this, tends to hit here. It is hitting here against the curve. Then it has to turn. So rather than turning, some of the power is being lost here at XC. Okay, this point. So this is your macro bending loss. So next is the micro bending. So the micro bending of the fiber axis, which is the core. The micro bending loss is due to the microscopic bends. You can see in this diagram, the first diagram. You have the whole fiber, we have core, which is being surrounded by cladding. So due to micro bending, you can see that the structure, okay, the structure, you can see that these are the microscopic variations, the microscopic bends inside the core. So due to the microscopic bends of the fiber axis that can arise when the fibers are incorporated into cables, the power is dissipated through the micro bend fiber due to repetitive coupling of energy between guided modes, leaky modes, or the radiation modes in the fibers. Okay, so whenever two or more optical fibers are joined together, it may result in microscopic variations of the core. Or when a fiber is coupled to another fiber, or to transmitter, or to receiver inappropriately, coupling will occur. So due to that, there would be power loss from the higher order modes. Okay. As the signal goes in this TIR fashion, it will take this microscopic bend, and it will move out of the core. So similarly, it will move in this fashion, whereas it will get distorted with the other frequency modes, higher order and lower order modes. So this is microscopic bending or micro bends. This is your micro bending losses. So any other queries or any other doubts, you can type in chat box. So next loss is the core cladding loss. So core cladding loss is due to the optical fibers composition having different refractive indexes. So always the optical fiber is made up of core cladding. Core is the inner where the optical wave is being propagated. This core and cladding will always have different refractive indexes. Such that total internal reflection occurs properly. Due to this, the core as well as cladding will tend to have some losses, which is different attenuation coefficients. The losses that occurs during the propagation of the optical fiber due to core is called as core loss, and during the same transmission, if it is occurs due to cladding, it is called as cladding loss. So the formula for finding the core cladding loss is here. Alpha Vm, the mode of operation, which is equal to alpha 1 P core divided by P plus alpha 2 P cladding divided by P. The power at core divided by the total power, power at cladding divided by the total power. So the P cladding divided by P can be found out by 1 minus P core divided by P. 1 minus of that. So the total core cladding loss is equal to alpha 1 plus alpha 2 minus alpha 1 into P clad divided by P. So if only cladding power loss can be measured, we can easily find the core cladding losses. So with this,